Hi, in this video, we're going to be talking about the average rate of change and the difference quotients, which sounds like something that we have never seen before, but it is actually something very familiar. This is the definition of an average rate of change. We're having x1 and f1, x2 and f2 that are different points. Our average rate of change is represented by this mess of stuff, which looks like something really complicated, but we know what an f of thing. That's a y, and this is another f of thing. That's a y. This average rate of change thing is identical to this thing. This is slope. This is talking about the idea of a slope of that function. However, not all functions are perfectly straight lines. And it's only on perfectly straight lines that we're able to find specifically that slope. But in terms of calculus, we want to know more about what is going on with the slope of a curved line, which is where average rate of change comes in. It's not perfectly following the line, it's getting an idea of what the line is doing. So let's explore that. In this example here, we want to find the average rate of change of h of b. I already know what it is because we've been doing this since middle school. I know the slope is going to be 7. So this average rate of change thing better spit out a 7. So when I do the average rate of change, I should get a 7. So let's find out. We want to figure out what b of 2 is going to be when b is 2, what is h of 2, and what is h of 10. I recommend finding these separately rather than plugging it directly into the average rate of change formula. So when I do 7 times 2 minus 4, plugging in that 2 for b, we get 14 minus 4, which is 10. So we know that h of 2 equals 10. And then we want to do h of 10. So what happens when b is 10? What happens when we put a 10 where the b is? So we got 7 times 10, which is 70, minus 4. 70 minus 4 will be 66. So that means h of 10 is going to be 66. So now I know h of 2 and I know h of 10. I found that before I start doing my average rate of change thing, but I know I want to do that eventually. So down here, I've got my x values or b values. I've got 10 minus 2. You can put these in either order. The important thing is these are both 10s. Those are both 2s. You plug that in, we get 66 minus 10 over 10 minus 2. That better be 7. 66 minus 10 is 56. Divided by 8, is that 7? It sure is 7. Well, that's what we wanted. We expected that value because we already knew what the slope is just by looking at this linear equation. In this example, we know that the slope should be 7. So we should get a 7 when we do from b equaling negative 5 to b equaling negative 3. In order to do that average rate of change thing, I want to do these two separately first before I start plugging it into my average rate of change formula down here. That'll just make my simplification a little bit easier. So h of negative 5, we will put a negative 5 where b is. So that'll be the 7 times negative 5 minus 4. 7 times negative 5 is negative 35 minus a 4. So we get negative 39 for what h of negative 5 is. It's going to be negative 39. I'll plug that in down here in a minute. But first, I want to figure out what is h of negative 3. So we replace this b here with a negative 3. So that's 7 times negative 3 minus 4, which will be negative 21 minus 4. Negative 21 minus 4, that's negative 25. So we know h of negative 3 is negative 25. Now that I know these two h thingies, I'm going to put them into this thingy. Remember, when you put them into here, it doesn't matter the order of them. All that matters is these are both negative 3s. These are both a negative 5 so that those match up. And you got a minus in the middle. Then we just need to simplify this down. We plug in our things. That minus minus becomes a plus. We've got negative 25 minus negative 39. We're all done simplifying. This better be a 7. So we get 14 divided by 2. Yep, that is a 7. So our average rate of change thing is producing what we were expecting. In this example, I can see why the average rate of change is important because this is a quadratic, and I don't know what the slope of a quadratic is because it's changing all the time, and it's not a straight line. So this average rate of change gives us an idea of how the graph is changing as we go from -2 to 0. Is it going down? Is it going up? I don't know. We're getting a rough idea of what its slope is going to be. So again, I want to figure out these two things separately before I plug it into my average rate of change formula. So I start with m being -2. I'm going to plug that in here, being careful to put the parentheses around that -2. If I don't have them there, I'll get the wrong answer on the calculator. I should get 4 plus 2 because that -2 times -2 is positive 4. 4 plus 2 is 6. So m of -2 is 6. So that's the first part of my average rate of change formula. Then I got to do that m of 0. So again, I'll plug in 0 where that x value is. M of 0 will be 0 plus 2, which is 2. So m of 0 is 2. So now I know those two values, and I'm able to plug it into my average rate of change formula. Remember, make sure it doesn't matter what order you put these things in. We just need to make sure that these are both 0. Those are both -2. You got a minus in the middle. Now we want to simplify this thing down. M of 0 was 2. M of -2 was 6. Our minus minus in the denominator became a plus. And we want to simplify this thing down. We get -4 over 2. So our average rate of change between -2 and 0 is -2. So that's roughly how this graph is changing between those 2 points. In this example here, I want to find the average rate of change of m from 1 to 2. In order to do that average rate of change, I want to first figure out what m of 1 is, then m of 2 is, and then I'm going to put those into my average rate of change formula down here. So we start with 1. We put in 1 where x is, so that's 1 squared plus 2, which is going to be 1 plus 2, it's 3. So I know that m of 1 is going to be 3. And then I want to find m of 2, so I want to put in a 2 where that x is for m. So I'm looking up here, replacing that x with a 2. 2 squared plus 2 is going to get us 4 plus 2, which is going to be 6. So m of 2 equals 6. Now that I know what m of 1 is and what m of 2 is, now I can plug it into my average rate of change formula. Could you do all of this stuff up top and like plug it all in right away? Yeah, but it kind of makes a mess. It's easier to just kind of like do the individual bits and then plug them in to your average rate of change later. Because now all I got to do is say, okay, well, m of 2, that was 6. M of 1, that was 3. So I can plug those two in. 6 minus 3 is going to be 3. And so my average rate of change of this function from 1 to 2 is 3. Taking a look at these examples actually on a graph shows why we get sort of different values from these functions. If we're looking at h of b is this, going from -3 to -5, we get that slope of 7. And same thing from 2 to 10. We get sort of that same sort of slope of the graph as we move from this point to this point, as we do from this point to this point. It's sloped the same way. When we look at this in terms of a quadratic, however, we can see that we're getting different things. From -2 to 0, we've got this line that goes down and doesn't quite follow the curve. It's approximating the curve. It's our average rate of change. In general, this thing is going down. It's not going perfectly down like that. But if we go from 1 to 2, we can see now instead of going down, we're going up. Again, we're not quite following the curve, but we're in general going up from 1 to 2. Well, in general, we were going down from -2 to 0. So that average rate of change is trying to get an idea of what is the slope of a curved line rather than where it's not very helpful finding the slope of a straight line. Here is where calculus uses the average rate of change in order to be more helpful. The difference quotient feels like, oh no, this is something complicated and new. Nope. That's just another slope. We've got our x at plus h and x plus h. That's our x2. And our x is our x1. The denominator gets simplified a little bit for us because that x minus this x is just an h. But it's doing that same sort of thing, trying to identify in general what is going on with our graph as we go from this point to a later point. And what calculus does is it plays with this h value and it tries to push that h value smaller and smaller and smaller so that we eventually find the slope at a single point, which is something that we can't do right now. We don't have the tools of that in pre-calculus, but it's what calculus checks out is like what happens when that h value gets smaller and smaller and smaller. To prepare us for that, we're taking a look at the difference quotient right now because it relates pretty well to what we're doing with functions. In order to evaluate this difference quotient, I want to get this f of x plus h. I already know what f of x is. They gave me that. But I want to figure this out first, and then I'm going to start plugging it into my difference quotient. So in order to find f of x plus h, I need to replace that x with an x plus h, making sure to put that inside of a parentheses. Now I can't just distribute that squared over that parentheses because I've got some addition going on in there. So this thing right here in the middle needs to be FOILed. I need to do an x plus h times another x plus h, and then FOIL those two things together, which makes this x squared plus an hx plus an hx plus an h squared. X times x, h times x is at hx, x times h is another hx, and h times h is an h squared. That minus 1 is just kind of like chilling on the end for right now. We can simplify this a little bit. We can put these two hx's together, but that's about it in terms of like simplifying that thing down. So it's a little bit of a mess, but at least we're just dealing with just that mess before we plug it into an even bigger mess, which is what we're going to do now. So we know that, and we know this from the start of the problem. We want to put those two into the numerator, and we want to subtract those two. Okay, so here's that mess. So I copied my f of x plus h, and then minus that other thing. See why we kind of wanted to simplify that down a little bit? If I had to do all of those steps and just copy this over and over, ugh. Instead, figure out that f of x plus h first, and then plug it into your difference quotient. Once we could go there, now we can try to simplify things down. I'm subtracting all of f of x. So I got to distribute this negative into that parentheses. So it gives me a negative x squared, and that negative and a negative make this positive. And then I'm like, okay, well, can I combine any like terms? Oh yeah, this negative x squared and that x squared, that becomes a 0. And this negative 1 and that positive 1, that becomes a 0. So those two are going to be gone. So let's get rid of them. Bye-bye. So now we just have that 2hx plus h squared. Okay. I want to try to simplify this a little bit more. So I say, oh, they both have h's in the top. So let's factor out an h from there so that we get this part. So, okay, that's factored out. Oh, now these h's cancel. So we're left with a 2x plus h. So that is the value of our difference quotient. F of x plus h minus f of x over h ends up being this nice little thing, 2x plus h. Awesome. In this difference quotient, they've done it a little bit differently. Rather than keeping these both x's like they normally do, they gave us some 2's there. Okay, well, that's just less variables for us to deal with, so I'm not bothered by that. But I am going to figure out what f of 2 plus h is and what f of 2 is first before we start plugging it into this thing, because that's just going to make my simplification a lot easier. So we'll start over here with the hard one. We put a 2 plus h in both of the places where those x's are. So we've got 3 times our 2 plus h, and then that 2 plus h also needs to be squared. We multiply that 3 into the 2 plus h, so 3 times 2 got us 6, and 3 times h got us this 3h. And then this thing, we can't distribute that squared over that addition. So we actually have to break this up into a 2 plus h and a 2 plus h, and this thing needs to be FOILed. So we're all done over here, but over here we've got that 2 times 2, that got us 4. 2 times h is going to be a 2h. Our outsides, 2 times h is another 2h. And h times h is h squared. We can do a little bit of simplifying here. We've got 4 and 6. We can add those together. That's 10. We've got a 3h plus 2h is going to be 5h. And then 2 more h's. That got us 7h. And then our h squared is just kind of hanging out. So that's our f of 2 plus h that we're going to put here. Then we also need to figure out what f of 2 is. That'll be a lot simpler. We just need to put a 2 in both of these spots. So 3 times 2 plus 2 squared. 3 times 2 is 6. 2 squared is 4. So f of 2, that's just 10. Okay, cool. That's a lot neater. Now that we know those two, we can plug them into our difference quotient. There we go. We replace that f of 2 plus h with all of this stuff. And then we subtract f of 2, which is 10. I always just kind of put parentheses there after that subtraction, just in case it matters. In this case, it didn't, because a negative 10 is just negative 10. But then, hey, that 10 minus 10, hey, that's just 0. So bye-bye tens. You can get out of here. So we just have 7 and an h squared. We could factor out an h from that numerator because that's a greatest common factor of the 7h and the h squared. And that makes these h cancel. We can't cancel them here, but we got to factor them out first. Once it's factored and we've got locked up all that addition, we can cancel. H divided by h is gone, and we just are left with that 7h. So that is the value of our difference quotient. That 2 plus h minus f of 2 over h is just going to be 7 plus h. Wow, that's nice and neat. That is the end of our video on average rate of change. The power of an average rate of change is understanding that slope of a curved line rather than the slope of a straight line. Whenever you're evaluating these average rate of change or difference quotients, I really recommend that you figure out the parts separately. And then once you've got all of those parts, then put them together into that average rate of change or difference quotient and simplify that down. It'll just make your lives a little bit easier. Thank you so much for watching. Bye-bye.